Okay, we're on chapter 11, keys, couplings, and seals, including splines. And I want to solve for you problems 4, 5, and 6. They're all related. And let's start with the statement for problem 4. It says a chain sprocket delivers 110 horsepower to shaft at a rotational speed of 1700 RPM. The sprocket has a bore diameter of 2.5 inches and the hub length is 3.25 inches. So from other considerations, diameter of the shaft and the hub are given, and there's here a generic statement. Problems 1 to 4 and 7 determine required key geometry, length, width, and height. Use SA10 18 steel for the key. If not, use higher strength, and unless otherwise stated, assume that the key material is weaker when compared with the shaft or the hub material. Okay. So problem 4. Let's see what's the best way of aligning this. So problem 11.4. Let's summarize what's given. So we have the power, horsepower, 110 horsepower. We have the RPM, and then we have the shaft diameter, capital D, 2.5 inches, and then we have the length of the hub, 3.25 inches. 25 inches. Okay. At some point we're going to need the torque transmitted. There is an appendix at the back of the book with conversion factors. It's page 829, but it's not listing the equation that we need, although I have it written here. You find it on next chapter. It's equation 12.1, and it says torque in pound-inch. You get it by multiply the power and horsepower with 63,000 and divide by RPM. So the torque now corresponding to this 110 horsepower is going to be 63,000 times 110 divided by 1700, and I have, as you can see, calculated here, is 4076.5 inches. Okay, this was equation 12.1. The key now, size, the shaft is less than 6.5 inches, so the key would be a square key. And we go back to table 11.1, and ours is between 2.25 and 275, so we have W equals H and equals 0.625 inches. So we have the key size. Now we need to calculate the required length of the key. And remember, there's this theory where design stress so the two considerations, shearing the key and bearing stress between the key and the hub or key and the shaft. The shear stress, you calculate it by dividing the torque transmitted with the radius of the shaft to get the force, the shear force, and divide the shear force by the shear area of the key. Calculate the minimum length, equation 11.2. Design stress will be the yield strength and shear of the key material divided by design factor, usually 3 design factor, and an approximation for yield strength and shear of the key material, which is ductile, is as half of the yield strength in tension. And then the bearing stress, the second part of this section 11.4, you assume that half of the key is inserted in the shaft, the other half into the hub. The bearing area is going to be half the height of the key times the length of the key. The design stress is yield strength of the key material divided by design factor. Now here is where things can branch. The theory assumes that the key is the weakest material, but you can have the hub the weakest material. So if the hub is iron, you look at the compressive or at the ultimate strength in compression for the iron material that you're dealing with. And that will be the design factor, and you divide the ultimate strength in compression for the hub with the design factor. Okay, so that will be the minimum required key length for compression. Now for square keys, which is our case, so for shafts up to 6.5 inch diameter, given this approximation, so it happens that from both consideration for square keys, the minimum length equation is the same. Okay, so when width equals height, the minimum length is the same. So it will be our case. So we can use this equation as is. The L mean of the key equation 11.5. So we have what, 4 torque transmitted times design factor over diameter of the shaft, or rather divided diameter of the shaft, yes, over width of the key and yield strength. So 4 times 4076.5 we'll see, times design factor, that's 3, diameter of the shaft is 2.5, 0.625, and haven't summarized this, but for SA 1018, the yield strength in tension is 54,000 psi. Okay, so we have 54,000 here. Okay, and if you do these calculations, you get 0.5798 inches. All right. Well, this is not, it is the answer to the problem, but is not the answer to the engineering problem at hand. It's too short. It's short. The key would look more like a little cube, and it's not the way keys are found on machinery. You want to have maybe 3/4 of the hub length of the key. So you adopt or use L for the key, maybe 2.5 inches. If needed, you can choose a softer material, maybe a non-ferrous, maybe aluminum, but definitely not even rounded to the nearest size of common size would be 0.625 inches. So a really a little cube, and you don't see keys fabricated as cubes, period. Adopt and consider using aluminum material Okay. Now, it's not part of the problem. So let's take the case where we have, so assume, is it double S? Assume hub of ASTM grade 20 iron. Okay, like in problem 3. So let's see how the it changes, how the problem changes. You're going to check first the ultimate strength in compression for the for this iron. So I'm on page 794, and the first entry is gray iron number 20, and ultimate strength in there's no yield strength, ultimate strength in compression, that will be 80 ksi. Ultimate strength in tension, not our case. So the bearing stress on the hub will be 80. Admissible was design factor 180, which is less than or rather more than the yield strength of the key material. But if we're to calculate from consideration of so with this one, compression, we say it's 80,000 psi. We can calculate the required length of the shaft, minimum required length from for compression. So I'm using equation 4, and I'm going to say L min from consideration of compressive stress at of the hub material. So it's going to be 4 times T, and then design stress is going to be the ultimate stress in compression divided by design factor, diameter and height of the key. Okay, so I have 4 times what was that, the torque, 4076.5, 80,000 over 3 times 2.5 times 0.625. Okay, so let's see, 4 times 4076.5 over 80 exponent 3 times 3, this goes above, over 2.5 over 0.625 equals 0.391 inches. Okay, well, less than from consideration of yielding the key material. Key is really weak, but when you have the case of maybe hub made of some polymer, some plastic, you would want to go this route. Okay, I guess this was problem 4. Let's move to the companion problem 11.5. 11.5, it says, so 5, specify suitable spline having a B fit for each of the application problems 1 to 4. Well, it will be problem 4 for us. So we have the same hub length, shaft diameter, power transmitted, torque transmitted. We need to select a spline, rectangular spline. So problem 11.5. Okay, and we go to the section that discusses splines, and the shaft diameter again is 2.5, so that's like this big. 4 splines, 2.5. So 4 splines doesn't look good. Even 6 splines is ugly. I would go with 10. My gut feeling tells me, you know, looking good for this big shaft, 10 splines should be the number. So N equals 10 splines. Okay, not design factor. Design factor is captured elsewhere. Remember, we have torque capacity when the bearing stress is limited to 1000 psi. So a design factor is there with the 1000 psi. All right, so for 10 splines and the fit B, we're going to see width of spline is 0.156 times the diameter. And then we have the height is 0.07 times D, and then D equals 0.86 times D. Again, D is 2.5 inches, the shaft diameter. Okay, so let's see. We have actually I have these answers results calculated earlier. So width is the value is 0.39 inches. Height of the spline is 0.175 inches, and then the minor diameter is 2.15 inches. Okay, 10 spline fit B, by the way. And let's even quote, so table 11.5. Okay, also need to calculate as part of the equation 11 the average radius. We have a formula somewhere. It's major diameter plus minor diameter divided by 2 again. And this is a 2.15 plus 2.5 over 4. This is 1.1625 inches. Okay. Equation 11.9 gives us the torque per torque capacity per inch of spline. So torque capacity is going to be 1000 times number of splines times average radius times height and times the length of the hub. Okay, so we have the length of the hub given 3.25 inches. So 10, the value we just calculated, height 0.175, 3.25. So we get the torque capacity in pound-inch. I have it calculated 6,611.7 pound-inch, which is greater than the value that we know, 4,076.5 pound-inch. So the answer is yes. The spline, the selected spline is okay. 10 fit B, all that. And there is even room to have some chamfers at the end of the hub. They're commonly provided to allow for an easier assembly. Okay, so this was problem 5, and the last problem from this group is 6. So 6 is, says design a cylindrical pin to transmit the power as in problem 4, but design so that it will fail in shear if the power exceeds 220 horsepower. So this will be problem 11.6. And now the torque, the maximum torque is twice the calculated value, so it's going to be 2 times 4076.5. Okay, so it's 8,153 pound-inch. And we have an equation we saw, or we remember from strength of materials designing or pins in double shear. Where is it? Disaster splines. There's the equation here for the required diameter of the pin. So D required, this is equation 19, 1119. So what do we have? 4 times torque over diameter times pi, I don't know why they put in parentheses, times design stress in shear. Okay. Let's use the same material, the SA 1018, a soft material, and so the design stress is going to be, remove that approximation, yield strength in, so we have the yield strength in tension, 54,000 psi. Yield strength in shear is going to be half of this, an approximation. So we have 54 over 2, that's 27,000 psi. And this is going to be the design stress, yield strength in shear, okay? So we have the torque. This is maximum torque from above. We have the diameter, 2.5. So we can calculate the required diameter quickly. So I have 4 times 8153 over 2.5 pi over 27 exponent 3 equals, and take the square root. Have 0.392 inches. Okay. So yeah, this is a numerical answer. Practical answer is find a drill bit. You don't want to special order drill bit. Find a drill bit that's closest to this. And it might not be exactly this. There's an option to choose a metric. Let's see what will be the metric equivalent. So times 25.4. It's very close to 9.96 millimeters. So you can use a metric 10 millimeter diameter metric drill bit in the material if it comes as a bar. Of course, you want to have a little bit of interference. You may need to machine slightly that bar. But there's the option you know, I need to show also the shaft. So you have the shaft, and you have the hub. And then here's the pin that will go through. And the pin now I need to erase because the line is no longer visible. So this will be the pin, and you can induce or fabricate the pin with a groove to direct the shear at the interface between the shaft and the hub. Okay, so the pin will have these two neckings or little grooves, and you can size it. There'll be a stress riser, of course. Some experimentation may be needed. So you can use standard diameter, and so could be 10 millimeters, but you can make this little groove to get it closer to the calculated value and run some experiments also. Alright, so I guess this was it. I'm going to scan and post the hand notes, and okay, I'm stopping recording.